Hey guys, welcome back. So we're finally doing some fun stuff with combination circuits. This is just an intro where you'll be applying your foundation in series and parallel circuits. The key thing about combination circuits is to be able to really simplify the circuit in terms of combining resistors. It's kind of like adding a bunch of fractions together by finding a common denominator and then simplifying the fraction to its simplest form. But even though you have a simplified circuit, it's really important to look back at the original circuit when you're calculating components like voltage and current for each resistor, because remember, the rules are very different for resistors in series and in parallel. So this video is a warm-up to combination circuits to help you build a foundation of strategies when you're approaching these problems. The more comfortable you are with being able to simplify a circuit and also be able to identify which rules apply to series and parallel resistors, the easier these problems will become. So thank you in advance for watching. I'll be posting more problems later. Okay, let's get started here. A combination circuit has resistors that are not in parallel, but also resistors that are in parallel with each other. So in this drawing right here, R1 is all alone, R2 and R3 are in parallel with each other. Let's say all the resistors have 10 ohms in resistance. I'm going to move this over to the right for a second. And like in the other videos, let's make a table where you can calculate the values of voltage in units of volts, current in units of amps, and also resistance in units of ohms at resistor 1, resistor 2, resistor 3, and for the whole circuit, which we'll just call T for total. So remember, I just said that all the resistors were 10 ohms, and the battery that I gave was 6 volts. So this is all the information that's given. So let's talk about what we have so far. The whole goal with a combination circuit is to simplify your circuit so that it looks basically like you only have one resistor or have resistors that are in series with each other. In the past videos, I talked about calculating total resistance, which is something we'll still do here, but I also want to bring up this concept of equivalent resistance, which means basically calculating the overall resistance from multiple resistors. So in this case, like you can't just add R1 to R2 and R3, but what we can do is isolate the resistors that are in parallel with each other first, focus on that, and figure out what their equivalent resistance is. So let's go ahead and draw another circuit where we just focus on the parallel parts, which are basically R2 and R3. Recall from the parallel video, you can actually find the equivalent resistance by using reciprocals. Let's just call this R23. So this is the equivalence of combining resistor 2 and resistor 3 together. You remember that this is equal to the sum of 1 over R2 plus 1 over R3. And then this calculation is fairly easy because all the resistors are 10 ohms. So we have 1 over 10 plus 1 over 10. This is equal to 2 over 10. If you leave your answer here, again, you'll either get 0 points or partial credit. What you have to do, if you remember the trick, is flip one side of the equation and do it also on the other side. So if you flip both fractions, you'll end up getting R23 over 1 is equal to 10 over 2, which reduces to 5 over 1, which is basically 5 ohms. So we can say that the equivalent resistor R23 is equal to 5 ohms. Let's just box that right now. I talked about simplifying circuits. Let's also talk about that right here. This was our original circuit. Let's talk about the simplified version. So the simplified version looks something more like this. So we still have 6 volts. Recall that resistor 1 still exists. Let's say this is R1. And then we have this other circuit that we call R23. And that's basically our simplified version. This is 5 ohms. And this is equal to 10 ohms right here. So let's just actually focus on this really quickly. So if you see this, it looks like a series circuit, and there's something you remember. You know that the total resistance in a series circuit is just equal to the sum of all the resistors. So here you could say R1 plus R23 will be the total resistance. So then you have the total resistance is equal to 10 plus 5 ohms, which basically is 15 ohms. So let's go ahead and fill in the table that we have. So now we know that our total resistance is 15 ohms. If you're looking at this table, you'll notice again, you have two components of Ohm's law, which means that you can solve for the third component. Specifically for this case, we can figure out the total current in the circuit. So let's go ahead and do that. So here we have I total. We're going to use Ohm's law, which is V equals IR, but specifically for the total circuit. So now we have 6 volts is equal to I total times 15 ohms, which we just calculated. Divide each side by 15, and then you end up getting 0.4 amps for your current, for your total current. So let's circle that or box it, and then fill out the table right here and say that this is 0.4. So what else do we know? Well, let's look at the circuit. So our original circuit is right here. We just calculated that the current in the whole circuit is 0.4 amps. So basically, you know that any resistor that's not in parallel will also have a current of 0.4. The current going through resistor 1 will have a current of 0.4 amps. When it hits this node right here, it runs into 2 parallel resistors. You know that the current splits when you enter parallel resistors. For this specific problem, it's actually pretty easy to calculate the current because the resistors are all 10 ohms. So in that case, you take this 0.4 and it'll split evenly, meaning that it'll go through resistor 2 in 0.2 amps. And then also the current here will be 0.2 amps. Because again, it splits evenly. Will this always be the case? No, this is just a simpler problem. Let's fill out the table now. So now we have 0.4 for resistor 1 because it wasn't in parallel with anything. And then resistor 2 and 3 will have 0.2 amps as its current. So again, the reason why I approach the problem this way, there's another way you could have done it, or a couple ways, is because you can now use Ohm's law to solve for the voltage at R1. And you can do it for R2 and R3, and they're basically the same numbers, so it makes life a lot easier. So let's go ahead and do that as well. Let's start with resistor 1. So at resistor 1, we're going to use Ohm's law again, but specifically with resistor 1 values. So voltage is what we're trying to solve for. We know that the current was 0.4, and then the resistance is always 10 ohms for this case. So then we have the voltage is equal to 4 volts. And then at resistor 2, which is also equal to resistor 3, we have voltage is equal to IR, but let's just say it's at resistor 2. The voltage should just equal the current, which is 0.2 times 10 ohms. So V2 is equal to 2 volts. Since R2 and R3 are the same, we can say that V3 is also equal to 2 volts. And then we can fill out this table. 4 volts, 2 volts, and 2 volts right there. And there we have it. Thank you for watching. I hope you enjoy this. Feel free to subscribe and like below. Thanks.